All right, lecture 19. This is the second lecture on chapter 8, vapor power cycles. Now I will review the ideal Rankine cycle. I will then review the performance parameters, in particular the thermal efficiency and the backwork ratio of this Rankine cycle. I will then add irreversibilities to the Rankine cycle, and then we'll go over the steps needed to analyze the Rankine cycle with irreversibilities. And then we'll include superheat, which is something that's always used in Rankine cycles, actually. So let's start with a little review of last lecture. This is your Rankine cycle. You take steam, which in the Rankine cycle by hypothesis is saturated vapor, at point number 1. You expand it isentropically through a turbine from 1 number 2. That does work out from 1 to 2 isentropically. This turbine then does its work, WT, so the power produced per kilogram of mass flow through the material, is the enthalpy difference between point 1 and point 2 positive. Positive because the arrow is this way. So now at point 2, you have vapor that has a certain quality. This is vapor at a low temperature, low pressure, but it has a certain quality. There's a certain fraction of it that's vapor, and you have a certain fraction of it that's liquid. So that's step number 2. Now we have to cool that. Well, that is to say, we have to take heat out of it. We're not changing its temperature, because temperature and pressure are fixed, but we have to take heat out of it to make the mixture of vapor and liquid entirely be liquid at the saturated liquid line at point number 3. That is done with the cooling water outside. Note, however, that the pressure in 2 and the pressure in 3 are by hypothesis the same. This is a heat exchanger, and it's essentially an open tube with no pressure drop across it, and only heat that comes out of it and comes out of the water that circulates here and goes in the water that circulates there. Idealized, of course, in practice, all heat exchangers have pressure losses across them, but we will neglect that. If so, then the heat that goes out, the heat loss rate per mass flow rate is going to be the change in enthalpy between point 2 and point 3. It's positive because the arrow is drawn that way. The third step, the pressure here is the same as the pressure there, but you see this other thing, the boiler or the steam generator, is also a heat exchanger. So again, by hypothesis, no pressure drop between these two. Because we know this is a high pressure side and this is a low pressure side. That is a low pressure side just as this. So we have to have a pump to get that water back to the pressure of the high pressure side. That pump between 3 and 4. Well, that pump takes work in with this arrow, and that work per second, or that power, is divided by the mass flow rate, the difference in enthalpies between point number 4 and point number 3. It is again positive with these arrows as indicated here. And finally, we have to heat this water, this is liquid water, at high pressure, back up all the way to the high temperature, high pressure version that we have sent in the turbine in 1. And that is done by adding heat to it that comes from the boiler and going from cycle 4 to 1 with heat in, with this arrow given by the change in enthalpy between this high enthalpy point 1 and this low enthalpy point 4. That's the ideal cycle. So let's summarize this. The work that we get out is the work of the turbine. The work that we put in is the work on the pump. So the net work that we get out of the system is the work of the turbine minus the work of the pump. Now, the heat that we get out in the condenser is here. The heat that we put in the boiler is there. So the net heat that we get is Q in minus Q out. And since it's a cycle, you know that the net work equals the net heat because there's no change in enthalpy through the cycle. Well, let's take a look in our TS diagram at our TDS equations. So the Q in is going to be the area C to 4 to A to 1 to B to C. That is Q in. That's your TdS equation. Q in is the integral of TdS. T is here, ds is there, so that is simply this area here. Q out, on the other hand, is the TdS equation as applied to the 2 to 3 transition. So basically, that is this. It's isothermal. That makes life easy. And the ds is simply that you have to integrate over this x-axis. So this is the Q out divided by m dot is here. Well, since the Q in was the total here, and the Q out is that, and the net work is equal to Q in minus Q out, that means that the net work is the area of the cycle in the TdS diagram that's hatched sideways this way. Very quick, obvious visualization of where your work is in a Rankine cycle. It is just the area in the TdS diagram inside the cycle. Now, in the PDV diagram, it was more difficult to explain, but it's still the same concept. What is interesting is that you have the exact same concept in the TS diagram. But to get that, you have to write your conservation of enthalpy, in this case, across the whole cycle. Okay, so now what is the thermal efficiency of a Rankine cycle? Well, it's the net work out, in other words, is this, Wt minus Wp, over the heat in. Well, the heat in, the heat that you pay for, is this entire thing. It is this, H1 minus H4. So when you work that out, you have W turbine is H2 minus H1. W compressor H4 minus H3 minus sign, because this is work that you have to put in. This is work that you get out. So the net work out is the difference between the two. And the heat in is H1 minus H4. So you can rework that a little bit. And it's 1 minus H2 minus H3 over H1 minus H4 is the thermal efficiency of your Rankine cycle. That is one very important concept, because that really determines how efficient your plant is, how much it will cost per watt of electricity produced. Something else that matters to the amount of power that you can get out is the heating rate, which is in fact the inverse of the efficiency. It's heat in over net work out, it's 1 over eta. That's just a word that you need to remember because it's used. Now, a new concept that is actually useful and very important, but not so much in Rankine cycles, that will be later in gas engines, in Brayton cycles, is the back work ratio. So the back work ratio is the ratio of these two guys. It's the amount of pump work that you have to put in divided by the amount of turbine work that you can get out. And in our particular case, it's H4 minus H3 over H1 minus H2. You can immediately see that because the pump work is going to be related to this little change here, whereas the turbine is going to be related to that big change there, you're going to be paying much less for your pump than you're going to get out of your turbine. The reason is fundamental. It's because your turbine work comes from a gas, a vapor phase, where the PDV is large because the dV is large. Whereas the work that you put in, the pump, you're compressing a liquid. A liquid is essentially incompressible, so the dV during the compression stage is very small, so that work is small. In a Rankine cycle, the back work ratio is generally large. The Rankine cycle does very well when you compare the work out over the work in. Not so the Brayton cycle, because in the Brayton cycle, which we will see in chapter 9, we're going to be compressing a gas and expanding a gas also, so this ratio now will be much less favorable. That's one of the main reasons to use vapor compression cycles. Now, we have to revisit these things. There are two things that are going to be changed. First of all, the cycle is extremely idealized. The real cycle has, of course, irreversible UTs in the turbine and in the pump. And of course, it has pressure losses across the heat exchangers, which we have completely neglected. So the rest of the chapter, we're going to go down the list of problems and then a list, a catalog of solutions to the problems to get the efficiencies back up. All right, well, let's start with the water pump. So I told you when we talked in chapter 4 about pumps, or when we talked in chapter 3 about internal energies and enthalpies of incompressible fluids, that most of the time the enthalpy of the incompressible fluid at pressure and temperature is not very pressure dependent. It is temperature dependent, so that you can, but if you even neglect that, it's mostly the same as the enthalpy of the saturated liquid at the same temperature. This cycle is the exception to that statement. In the case of the pump, the pressure difference between 3 and 4 is quite important. So if we're looking at the pump, we have the heat losses in the pump, of course, and then we have this change in enthalpies, and we will have irreversibilities, but I can work this out. So let me take my PDV and my TDS equations. TDS is du plus PDV. du plus PDV plus VDP is dH minus VDP. Work that out, and you have that the heat is dH minus VDP. This is dH, of course, is H4 minus H3. And here you have this integral of VDP between 3 and 4. Now, V doesn't change much with P, but dP is very large. So actually your fluid in the pump heats up. And you could see that in the idealized cycle. This temperature increases a little bit. That is not due to simply irreversibilities. That is actually due to the term in the TDS that's due to dH minus VDP. That's here. Okay. Now, that means that the work, which is the integral of the VDP, is V P4 minus P3. So there is a correction to pressure, and that is the work that you're going to have. Note that this is the inverse of what we have generally. Generally, you have the work that is PDV, not VDP. But here, thanks to that, right, this is the enthalpy change, this is the heat, so then this has to be the work. The work is a specific volume times a change in pressure. We prefer to do it that way because the specific volume doesn't change much with pressure. It's an incompressible fluid, but we can find it. It's a saturated value, the value for the saturated liquid. And these are things that are very well known because they are very large differences, because it's the difference between the inlet pressure of the turbine and the outlet pressure of the turbine. So this is a much more accurate way of calculating the pump work than the classic PDV, simply because in the classic PDV, the dV is small, the P is very large, but dV is small, so you have no accuracy. Here, you have accuracy. So that's one subtlety. This is an equation you actually probably need to remember because it's hard to derive, and you'll find it in your book. All right, so now we have everything for the Rankine cycles, and in class I'll go over exercises, and this is all nice and well. But we don't really use Rankine cycles. So one has to look at ways to improve the power. And so we go back historically again, and we look at the very first engine, which was the Newcomen engine, which worked between a cycle where, well, let me roughly go here. This was roughly 100 degrees centigrade, and this was roughly ambient temperature. The reason is they couldn't take very much pressure on their old boilers, they would just blow apart. This is outside air, or outside temperature. So this temperature difference is small, so this amount of work that you could get off a Newcomen engine was small compared to the enormous size of the thing. And so you have these things that were sized like a building, and that would make 5 horsepower. So what does one do about that? Well, there are 2 ways to increase the amount of work. So remember, the amount of work is this area under the curve here. And so let's compare a cycle that goes from 1 to 2, 2 to 3, 3 to 4, 4 to 1. Okay, let's say that's 100 degrees centigrade. Suppose now that you are living in 1711 and that you have magically come up with a way to make a steel vessel that can take a higher pressure and therefore a high temperature. So you go from 1 to this one. Well, so are you going to get more work? Well, your cycle now go from 1 to 2 with a much higher temperature difference, 2 to 3, 3 to 4, and 4 back to 1. Well, the area under this curve isn't really all that different from the area under that curve. So this machine is not really all that much more powerful, in spite of the fact that you have to increase the temperature at the boiler. And the reason is the shape of the vapor dome. The vapor dome becomes narrower close to its top, so that as you increase the temperature, you also decrease the entropy, and you get an area that is higher, yes, but narrower at the same time, so you lose here what you gain there. So increasing the temperature of a Rankine cycle to get more power is not a good idea. The really good idea is to decrease the temperature of the condenser rather than increase the temperature of the boiler. Because now, if you can say from this point, you were going here, 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 if you could get to a condenser that works under atmospheric pressure and at lower temperature, for example with water cooling, then you add yourself this much area, and in fact you have a net gain of area. The reason is that, again, the shape of the vapor dome is such that you have made the base wider here. The other thing that you have improved is the Carnot efficiency of the whole thing, because you go from a hot temperature to a colder temperature that is lower. And Carnot is 1 minus T hot over T cold, 1 minus T cold over T hot. So one very efficient way to increase Carnot is to decrease T cold. But you win much more by decreasing the temperature of the condenser and the pressure of the condenser than by increasing the temperature at the boiler. The guy who figured that out is James Watt, and he got a British patent on it in 1775, and that made him extremely wealthy. This was an extremely well thought out machine. Now, if we look at an actual implement, here is a Newcomen engine. So you see the piston, and in fact, there are the valves. So these are valves. There is somebody, a guy, who manipulates a valve up to let the steam in, down to let the steam out into ambient air. So that's Newcomen engine. The Newcomen engine works where this is atmospheric pressure. And this is a Watt, James Watt's engine at the same museum. So the piston is still here. The valves, hand-operated valves, are still here. But the cold side condenses into this spot. So here in this trench, this was a canal, in this trench is filled with water, and the cold side is condensed from the first cylinder, the main cylinder in which there is a piston, into a condenser cylinder, and thereby gaining a lot of power. Note, of course, that you have more valves, but a single person can handle 2 valves. It can also handle 4 valves, because these engines go very, very slowly. Okay, the next step then is to try to get a Carnot cycle out of a Rankine cycle. So if we were to try to get a Carnot cycle in a TS diagram, we would simply go from 1 to 2 in an isentropic, and that hasn't changed, and condense it, but instead of going all the way to pure liquid, we would stop halfway so that the pump then would, the pump and the generator would get us straight from 3 to 4 back to 1. Okay, so this 3, 4 to 1 would essentially go 3, 4 to 1. All right, so what goes on with that diagram? So this would be very interesting, but we have 2 problems. The first problem is that we have here a mixture of liquid and vapor, and we have here again a mixture of liquid and vapor. And if you have a turbine with blades and a pump with blades or vanes, the pump works on the vapor and on the liquid at the same time, but it rotates. And so the droplets of liquid are going to impact on the blades and on the vanes all the time. That impact creates an erosion on blades and vanes, which makes the whole machine wear out very quickly. So it is really not a good idea to have a two-phase mixture in your mechanical machines because they erode blades and things. So this is something one really wants to avoid as much as we can. In the Rankine cycle, we had this one, but at least we didn't have this one. We were pumping out pure liquid. The second problem is that we have these temperatures more or less fixed by the possibilities of our boiler. Now, if you increase this, your vapor dome gets narrower and narrower, and so your Carnot cycle increases its efficiency, yes, but it decreases the power output. So ideally, you would even have your Carnot cycle to go as high as possible. So you would go to the critical point. That would be the best you can do, the most efficient machine, but also gives you no work. That's a do-nothing machine because you have no area left under the curve. So in the Carnot cycle, yes, you can make it, but the more efficient you make it, the less work, the less useful the machine is. So that is not so good. The third problem with all these cycles, and we will come back to this. Here is the combustion in your steam generator. You have a flame in your steam generator. A blue flame is typically at 2000 degrees centigrade. This is 500 degrees centigrade and you get no work. This, in a Carnot cycle, you would have to limit at 350 or 400 degrees C. The temperature between 2000 and 400 degrees C is purely lost. So you are going to have a poor Carnot efficiency if you compare it to the temperature of the combustion gases anyway, because T14 is much cooler than the combustion gases. So we really don't want to work either here nor here, and we actually don't want a Carnot cycle in vapor compression, in a vapor power cycle. To this, we add turbine and pump irreversibilities. So we know that WT is H2 minus H1, WP is H4 minus H3, but you really don't go from 1 to 2S. You really go from 1 to 2 with a little production of extra entropy that you have here, which is characterized by the isentropic efficiency of the turbine, H1 minus H2 over H1 minus H2S, which has to be smaller than 1. You know, in the same way, that the compression is going to get you not from 3 to 4S, which will be isentropic, but it will cost you more work. It will cost you from 3 to 4, and you have a turbine efficiency, which is H4 minus H4S minus H3 over H4 minus H3 smaller than 1. All these are inefficiencies that we will encounter in the machines in the cycles. And now finally, every practical cycle works with superheated steam. We don't work from 1 to 2 with saturated vapor here. We go in the superheated steam, and we're going to even push the superheated steam as high as we can so that this point 2 come as close as possible or even beyond the saturated vapor curve is not the cold side. We really want this transition from 1 to 2 to happen here in the saturated vapor regime, because then our turbine works only on gas, and we avoid this erosion of the blades by having the turbine work on a mixture of gas and liquid, whereby liquid particles, droplets, impact the blades of the turbine and erode it until there's nothing left. So that's the most important reason to go to superheated steam. There's another reason, of course. As you increase your absolute temperature on the hot side, you increase your Carnot efficiency, and in reality, you increase the area under your curve, so you increase the power output at the same time. Now, of course, you don't reach Carnot efficiency because in the TS diagram, if you're here, the transformation is not horizontal, but that's okay. You're better off having blades that stay alive for a while than having a more efficient machine that does no work and breaks down. So that's the end of this lecture, and we'll look for solutions in the next lecture. Thank you.